Hello everyone, welcome back. We're building self-driving cars here in a simulator. So anyone who wants to stay on, they're welcome to. Today we're talking about how we can hook up the Carla Simulator to a reinforcement learning network. So I picked Stable Baselines3, which is a free available framework that you can download. And what you need to do is here. I've actually created a set of requirements that you need to download in Python to get everything going. And I think Stable Baselines 3, which you see here, is using PyTorch. So that's why you also see this item here, PyTorch. So from any other house, from the housekeeping point of view, I've got a separate folder here in my self-drive directory on my GitHub. And here you can find this requirements file that you can get all your Python libraries from, or according to, I should say. And then we've also got some example code that shows you how to start training your models using Carla. But first, we need to go through what is reinforcement learning. This tutorial is not meant to explain in detail from scratch what goes on in reinforcement learning. Let's just say it's a thing that essentially manages an agent. Imagine your car is an agent. So the algorithm or the policy that you're trying to train is looking at what comes out from your environment, like for example, what reward you're getting from each step. Like each step is just one cycle in the simulator. So you get one image from the front-facing camera, and that is our observation space. Imagine we're using semantically segmented images from the car front-facing camera. That's our observation. So if you do something in the environment, like if the car does something, the output of this is this image. What is also output from one step is a reward. Like, has it done anything that is worthy of a reward? Or do you need to punish it for something? Because, for example, it crossed a lane marking that it's not supposed to. So a reward and observation space are two outputs that are coming from the environment. And then on the input side is whatever comes in, or whatever the variables that you're trying to play with. And obviously in a car game, it's a steering and throttle. Throttle is probably not, it's a bit simpler because it's kind of on and off. It's more, you can define it in a simpler way, but steering needs to be organized so the car can steer straight and go left and right. And there is obviously a variable degree an input that you need to give the car, and it needs to be manageable. So you can't just say left or right or straight, because the car will be moving in a very jagged fashion. Hopefully you get my point. So the steering input is more like a continuous kind of input where, imagine you can go as to Carla inputs, you go from -1 to +1, where 0 is straight. So any of those may represent your steering input. So the objective of the algorithm, the reinforcement learning algorithm, is you go in through a number of steps. And we also need to talk about steps and episode. Say episode is like one game, or the car is set up and it's trying to do things and trying to get to another destination, for example. And then until it crashes, it's one episode, okay? So when the car crashes and you need to restart again from the beginning, that's the end of an episode. So one episode is the car is trying to sort of get from point A to point B, as an example. And as it does get there, you go through steps. So one episode is made up of a lot of steps, potentially. It could be very short because the car can crash immediately into something and your episode is finished. But the structure of steps in episode hopefully makes sense. So as within one episode, this is going through the loop of each step. The algorithm here is trying to learn how it can vary the inputs, like the steering and throttle, to achieve more reward. So it's looking at what happens in the past when it tried doing certain things and what reward was. And also it's obviously looking at the observation or the image, and hopefully it tries learning from it in combination with reward, like what to do in certain situations. So that's reinforcement learning in a nutshell. So if we go back to the code, you need to define your environment first, right? Which is the actual code is here that we'll get back to later. But to start with, I wanted to show you what the environment should be, kind of what in a nutshell, what the environment should be made of. And as usual, you start with all necessary imports. And then the main thing you define is, unfortunately, fortunately, we go into object-oriented programming here, where in Python we define classes. And we define a class for our environment. And that environment has to follow certain guidelines, because we're trying to make it work with the Stable Baselines framework, which will, train the agent automatically. So we don't need to worry about how we set all of the mechanics of how reinforcement training or learning should be done. So that's what Stable Baselines3 will do for us as its own network. So all we need to do is to make sure we define our environments according to what Stable Baselines3 is expecting, okay? So we need to obviously have the init method, and this is where we connect to our simulator and the usual stuff. It's like initial, like we start training. To start training, we need to connect to the simulator, and we need to also define our action space and observation space, which is going back to these things. So we define what is our action space is, like how steering is can be coming and how it's represented, and what our observation space is, or the output image of our camera in this case. Okay, so we action space, observation space, and then we do necessary establishment of the environment. In our case, mostly it's connecting to the simulator. The next necessary method that we need to define within this class is a step. So it's the lowest level of our looping, like what actually happens every time. And it has to return things in this order. So it will have to return observation defined in accordance with this, and it's effectively our image in pixels. It has to return the reward, the actual numerical representation of what reward is coming from this step. Whether the episode is finished, so for example, if a car collided with something, we say done is true, and we return this done variable as a true. So the environment is not sent into the next step. It's finished and it will go into the next episode, okay? And then this sort of empty curly brackets is because it's according to the stable baseline. So you can return certain things from here, but we just don't use it, all right? And then the last necessary method that we need to define is reset. And here we telling the environment what happens every time we start a new episode. So remember, we're connected to the simulator. We're overall connected. We're doing training, but every time the car crashes, for example, we need to do a reset. And in reset method, we do the spawning the car, attaching sensors, and everything that, you need to do at the beginning of each episode. And then we return the camera of the attached sensor, or the same observation as we return from the step, okay? And that's pretty much it. And if we go into the actual environment that I've created for this, so you see we've got imports, then we define certain constants. Like for example, we assigning maximum seconds per episode as 25. This is just a restriction because so it doesn't take too long to go through this training. Then we obviously define our image parameters for the camera view that we're passing on. Then we define our class. The gym reference here is an environment that is used in Stable Baselines3, so that's effectively just inheriting the structure of that environment from gym. Excuse me. Then we're setting up the constants within the class, because every time we start the environment, all those constants need to live within the instance. And then we go into the init method. And here, the most important thing for us is we're defining action space. So what I was trying to do before, I was trying to use steering as a continuous space, which is defined as box, or, it could be anything from -1 to +1. And what I found is very hard to, I didn't have like years of training time to see what's happened, but the car started from, the steering will be in all the way to the right, which is, a value of 1. And like for a couple of days it was going and it wasn't trying to get to anywhere to being straight. So I decided that I will go into discrete or several possible values for the steering wheel. And I defined it as 9 possible values for the steering and 4 for the throttle and braking. And within the step method, I actually define which values correspond to what steering angle. Okay, this is where I interpreted. But in the init method, you need to define what sort of structure of your action space is. And then within observation space, you just do the normal image. It's a height and width, a number of channel, nothing really special here. You can just copy it. Then we connect into the simulator, setting up all the parameters of the simulation. I was trying to play with synchronous true, but for some reason it wasn't working, so I kept it as false. So I'm not sure if the delta seconds, in my case, like the frame rate effectively, which is 0.2, whether it's effective or not. Then I defined the cleanup method, just, what happens at the end of the episode. I need to clean the car and destroy any sensors at the end. And then my step method is effectively just interprets what action space, how it converts to the steering and throttle, and then applies those values to the car. Here I've also got like every 50 steps to print what the value of steering and throttle is, so you can see it if you're interested what the car is doing at the moment during training. Then I get the car's speed. I also get distance travel from the beginning of episode, because it's used to in reward calculation. Then depending whether the camera is set on and off, I show it here. So during training you can actually display the what you see from the camera, so you get an idea what the car is doing, which is great. But then when you're confident in your approach, you can turn it off, and it could save you some time, maybe, but not much. And then we get to how we calculate the reward. And here, I also found that the car just loved getting into continuous chasing your tail kind of thing, going around with the steering being locked up all the way to the left or to the right. So I defined a couple of things to actually capture that and punish for that in the reward calculation. But the reward calculation is essentially here. You can make it as you wish, and that's where I suppose most of know-how of how to do reinforcement learning, this is where the guts of it is. You essentially trying to reward for good things and punish for bad things. And in this case, if you get a collision, and I've got a collision sensor set up on this time as well, the episode ends and we penalize by 200 points negative, okay? Or the next thing for steering lock longer than 3 seconds, we also penalize by 200 points and also end the episode, because it's just not right to at this point to have the steering locked up all the way to the left or to the right. And then if the lock duration is longer than 1 second, we're also punished by 50 points, but we don't end the episode. So it's like, just giving it some hints that it's not good to have the steering turned all the way left or right. Next, you can reward for the agent to achieve certain speed. So, for example, you can penalize for the speed being below 10 kilometers an hour by subtracting 10 points. Then you can reward if the penalized by only 3 points if it's less than 15. But then you also need to make sure the agent does not begin to speed, and then that's when I put this thing where it's over 40 km an hour. Then you also put quite severe penalty on that, because it will most likely crash at that speed. And otherwise, if it's within a good range, you'd give it 2 points, okay? And essentially each one of those steps, they just start with 0, and based on each of those parameters, like the steering, like collision, the speed, the distance travel, you just increase or reduce the reward subject to how you want to train the agent. Now, guys, I noticed this little boo-boo as I was preparing the video for publishing. It used to be like this, and as I was watching it, I was like, ooh, I was ready to scream, because if it gets through this point, everything above it will get overwritten to 1. And the correction here, of course, is reward +1. That's how it should be. And again, another lesson, the reward mechanism is the paramount for reinforcement learning, and you have to double and triple check it every time, okay? That was my lesson from this. I had a big lesson for myself. Which is you get here from your sensor, and you normalize it by dividing each pixel value by 255, so it becomes from 0 to 1. Then you return your reward, the done variable, whether it's finished episode or not, and that's pretty much it. And in reset is where you spawn a car and you attach sensors to the car. And in this time, we've got semantic segmentation and collision sensors attached, okay? And then a couple of supplementary methods, like the actual processing of the image, very similar to what we used before, the ones that I used with the lambda, listen.lambda for each sensor. So they refer into collision data, like this method here, and process image for our camera, which is here. So it's very similar to how we've done before. So you see, relatively short code. So that is us defining the environment. The next thing we need to do, we don't run the script itself. The way we use it is we have another script that we do for training. And that's where we also import stable baselines, and we're going to be using PPO algorithm here. There are a few that you can explore and try, but this is the one that is generally recommended by this kind of task, and I've seen other people using in their examples. And what happens here, we're setting up certain directories, and then we create an instance of the environment that we defined before, and you can see we import it here. So from car environment, which is the name of that file before the .py extension, okay, we import the environment, and now we create an instance of that environment. Then we run reset. We define what the model is. This is where we use these stable baselines sort of definition. This is where we use that library, and then we define time steps. And time steps is how long do you want the training to go. It's sort of as it goes through episodes, it counts how many steps each episode was, and it sort of keeps track of how many total steps it needs to go through. So, for example, in one episode you can have 100 steps and then it crashed. In the next one you can have 50, so it's 150, and it keeps tracking it up until it gets to that number. And you can also have several iterations of training, like for example, within 3 just go over 500,000 steps. And this is where you save your model when it finished training, okay? So and your model will be saved in the directory structure, like here. So if I go to my self-drive directory folder, so I've got the models here. So those are the timestamps that are defined by whenever the file gets or folder gets created, and within that there will be your model. Let's find the one that has something inside. Ooh, interesting. I wonder why is that. This folder is empty. How is that possible? Okay. So there were definitely models before. All right. So when you kick off, you obviously need to have the simulator running, and then when you kick it off, this happens. So this is where you can see the preview of what the car is doing. And one thing I should highlight is it may be quite buggy, and not in all cases you'll be able to work with this, because you can see I've got some warnings coming from the thing, and I definitely destroy at the end of each episode. I destroy the cameras and any cars in the simulator, but it still doesn't like it, and it says this sensor went out of scope, or this object, which is probably got something to do with how stable baselines, 2 separate environments, interact with each other. So on one hand you've got Carla and the simulator running, on the other you've got this thing. You also have this warnings list. This IO operation has been aborted because like, it's weird. And previously when I attempted this, it actually led to simulator actually crashing. So I'm running 13 version of 9.13 version of Carla here, and everything is set up to run with that version. So hopefully you can try it with 14, but there is a lot of changes that you need to do to make sure everything else is aligned to 14. But anyway, hopefully you get the idea what happens here, and we can also see that in reality the agent is crashing very quickly because well, obviously it doesn't know what to do. And I let it running for a couple of days, and it was still crashing hard. But I suppose the objective of today is just to show you how to get it started, how to hook up Carla to the Stable Baselines3, and how to use them together. Once you get them going together, you can try changing like the reward structure, and maybe do additional things to help the agent learn what to do best. And you can also see that periodically it goes into this, it gives you these snapshots of what's going on, like how many total time steps. We've gone over 2,000 by now since we've been running this just during the tutorial. And then we can see that we negative on the reward. So this is episode average reward per episode, and it's about 210. So obviously it's crashing at the end, which is it gets minus 200 or 300, whatever that punishment is. And so at the moment it's just doing extra processing and training, like trying to work out the policy to control the steering wheel and the throttle. Okay. All right, so what else is there to say? I should probably show you. Let me just cancel any of this running. Imagine you've trained the model. How do you test it? So I've also got a script here that opens a model. Like if you've trained a model here, say for example, you've been training it for a couple of days and it went into this folder, which you can, see what's in your what's on your machine in the drive in those folders, and the model itself will be trained in one of these, .zip files. Okay, that's how it saves models. So you, excuse me, load it by using this command. And then for 5 episodes, you can just see how it performs. So the way you test it, you just run this file, obviously tweaking to your names, to your folder names and model names. And it shows you, like it prints a reward from each episode, and it shows you the total, right? And you see it's crashing at the end, and that's how it gets minus -200 at the end. So it's gone through several episodes here, and you can see reward from each one of the steps that it's gone through. You can actually, by scrolling through, you can see how many steps it's gone through. And like hopefully, if you get to a good model, you can see that it will be performing a lot better, and hopefully it will be running certain distance within the simulator. The other thing I wanted to show you is you can also continue training a model, which is a very cool thing. So say, for example, you got it going for a few days, and then it's looking promising. You can then stop it, maybe change your environment a little bit, maybe change your reward policy slightly, and then you can continue running it. So it's using very similar code to what you've seen in the test when it opens a saved model. And because it opens a model, you can then go into training the model as well. So it effectively will be continuing training the model rather than starting from scratch, which is another very useful thing in this context. Okay. All right. So this has been quite extensive. Hopefully it was useful. I thank everyone for watching, and whoever stayed up until this point probably already subscribed. But if you haven't, then please do so and share it among your friends. Thank you, and I will see you in the next tutorial.